welcome you guys to the first part of the today's webinar series, where we talk about the principles of applied flow assurance and how it's important for us in the oil and gas industry, and how we can utilize it to solve like different challenges that we might face during production or injection. Surface connections and how it's imposing issues for us regarding the flow assurance. And the second day, we'll be talking about the wells in general, oil and gas wells, to be more specific. So my name is Nashat Omar. I have been working in the oil and gas industry for more than 9 years. I am experienced production engineer, plus I have experience in applied flow assurance. I started my career by working for Schlumberger as a drilling engineer, and then I shifted towards production engineer career. And currently I'm working full-time instructor. Plus I do a lot of courses. I do Python, I do production, and I'll do flow assurance. In my experience, I had some experience with drilling, plus some more experience with data management using Avocet. So let's see what we are going to talk about today. So the first thing we'll talk about is the production system itself and how we are producing hydrocarbons. And once we've dealt with that, we will be shifting and moving toward the flow assurance and what's the type of issues that it might impose. And then we will talk about what data actually is required to do some flow assurance modeling. Plus, we will take a look at the differences between the dynamic or the modern plus versus the classical flow assurances approach, and which one is best. Plus, we will take a look at 3 case studies. The first case study is going to be the train slugging. The second case study will be modeling a production test separator and how different wells can affect the performance of a given test separator, and what's the challenges in that area. Plus, if we have some time left, we will take a look at the wax deposition and the wax modeling. So if we take a look at the production system, actually production system is any given system that can deliver hydrocarbons from the source to the destination or to the target. This in our case, this can be the production which starts from the reservoir and ending up at the processing facilities or ending up at the tanks itself. The production system, the core of the production system actually is the flowing fluid itself. The flowing fluid is the single common thing in all of the components in production systems. And some production systems has like different components or have like an extra components that other systems do not. This is basically due to design and operational challenges. And if we take a look at the basic components of a production system, we will see like major production systems it's actually consist of the reservoir, which is the source of all hydrocarbons. The reservoirs usually, they sit underneath the layers of the rock, and humans drill wells to produce that reservoir. To this day, wells are the single most economical thing that can be used in order to produce hydrocarbons. So far, we only have wells that can extract commercial oil and gas. Maybe in the future, we will have another technologies, but for now, we only have wells that can extract oil and gas production. The other part of the production system is the surface connection. Once you get your fluids, which is the oil and gas or any mixture of these 2 components to the surface, now you will have a challenge that you need to deliver these hydrocarbons from the wellhead or the the top or the top of the well to these processing facilities or these production facilities. This is known as a surface connection. Surface connection can have lots of components. For example, it can contain separators, knockout drums. It can contain inline heaters and pumps and compressor, depending on the specific configuration and specific operating environment of a given field. However, the more the components you have, the more the challenges of modeling you will face. A production facility is a must. Plus, you will have storage facility that you can store all of these produced hydrocarbons. So now let's take a look at what's a flow assurance. A flow assurance is actually is an art more than a science. Basically, flow assurance is the art of dealing with oil and gas production or any mixture of oil and gas and other fluids, and through wells and surface connection in the most economical way and most trouble-free way. So flow assurance, actually, the study of flow assurance will tell us a lot of things about our field and our assets. So the first thing is actually when and where does the problem occur? So flow assurance, you can think of flow assurance as a great tool, a great tool set that you can use to diagnose all of these problems that you are facing in oil and gas assets. So the second thing that flow assurance tells us is actually the fluid behavior and the different patterns that occurs in the field. For example, if you are having slugging flow, or maybe you're having annular flow, or you're having transition between different patterns, once you use flow assurance, you will know what's the cause of these types of instabilities during production, plus the proper remedials for it. The third thing, actually, once you know how to do flow assurance, you will know how to distribute fluid properties along the flow path. Because you can see along the flow path, which starts from the reservoir up to the tanks on the surface, the pressure and the temperature actually varies greatly. So once the vary in pressure and temperature occurs, the fluid properties will change. Once the fluid property changes, actually this imposes a great issue for us. Plus, flow assurance will enlighten us and gives us insight on the capability or the capacity of our production system and how efficient we are running. Plus, the most important thing in studying flow assurance is we will know, or we will estimate where the deposition and the plugging will occur in our production system. Is it going to happen in the wells, or is it going to happen in one of the vessels on the top, in the surface, or in the surface connections? So all of these questions, flow assurance will help us to answer. One of the most important issues that we have in oil and gas industry is the decline of the reservoir pressure. So as the reservoir pressure declines with time due to the depletion of oil and gas reservoirs, this actually will impose a very big challenge for us, because once the reservoir pressure declines, all the fluid properties will change. So the decline of the reservoir pressure actually can be studied from the eyes of the flow assurance, because the decline in the reservoir pressure will give you various problems at various times or at different times in the life of the field. And it's very hard to predict if you do not know the right techniques of flow assurance. Plus, the final thing is actually we can study the effect of the terrain or the effect of the geography on the production capability and the production system itself. So if we move forward to one of the most prominent and one of the most dominant issues in oil and gas industry, which is the deposition and the plugging of heavier compounds or heavier components from the production or from the flow stream. Actually, the modeling and the prediction of deposition and plugging is one of the most sought after techniques that's used in flow assurance. And for example, deposition and plugging of pipelines and wells are not desired because it can produce MPTs and it can increase the intervention and the remedial cost. So engineers and specialists, they try to avoid these conditions that will lead to these types of issues. So most frequently modeled deposition issues or the deposition types are wax, asphaltene, solids, and hydrates. Plus, sometimes scales are modeled as well. However, the wax, asphaltene, and hydrates are the most common issues in most of the oil and gas fields. However, they usually do exist together. For example, wax and asphaltene, they usually exist together as a mixture. So it's very important to study all of these components and to understand the different issues that we will face in oil and gas production. So let's take a look now at what data is required to do all of these flow assurance studies. So the first thing required is the daily data. So if you have like a high quality daily data that's reservoir, that's wellhead pressure, wellhead temperature, and phase wise flow rates like Q oil, Q gas, and Q water. So this is very important, and this is the very first step in creating flow assurance studies by knowing all of these data. So once you have all of these data, we usually try to extract trends, or we usually try to extract analysis from these data so we can actually identify if there's some problem occurring in our assets or not. The second group of data required is the sporadic data, or data that's event based. For example, surveying reservoir pressure, this is a sporadic data. This is event based. This is not captured daily. It might be captured twice a year or once a year, and some field they might do it like 2 years to once every 2 years. So it highly depends on the operator and its operating philosophy. Plus, we will have the PLT, which is very beneficial for flow assurance because it will tell us exactly where our production is coming from. This will hugely benefit us into matching the data. Plus, if you have other sets of survey, like static grading survey and dynamic grading surveys coming from the wells, from producing and shutting wells, you can use that as well to create and tune and match the models. The third group, or the third category of data needed is the fluid data. Fluid data, actually, what you need is high quality laboratory data that breaks down the single carbon composition, or breaks down the distribution of carbons, which is methane, ethane, propane, and so on and so forth. Plus, once we have all of these distributions, we can plug them into fluid models that are black oil and equation of state. Either one can be chosen. However, the more the complex the issue, the more the fluid model should be complex, meaning that we will be leaning toward the equation of state once we have these complex fluids in the field. For example, volatile oil, gas condensates, and any other issues like wax and asphaltene. We usually tend to model these using the equation of state. Plus, the study or the collection of fluid data actually will help us into determining or deciding upon the deposition envelopes. Deposition envelope think of deposition envelope are just sets of pressures and temperatures that you use actually to know whether or not you are actually producing in a problematic area. For example, if you have like specific pressure and temperature in the reservoir, and that specific pressure temperature it's favoring the deposition or wax or asphaltene, you will predict that issue. However, the severity of that issue, it will not be provided using the fluid data. You need a more sophisticated and more integrated flow assurance studies to know that. And the final and the most important thing is the structure of the surface and subsurface connections. For example, if you are modeling a well, you will need all the well configurations like pipeline, tubing sizes and the casing diameters and the materials behind the casing, etc. And if you are modeling like pipelines in the surface and assets like pumps and compressors, you have to install those as well in the model, so you can actually predict all of these different issues that might arise by installing these assets. The daily data acquisition is very important for us to know if whether we are having flow assurance issues or not. For example, one of the most important things to monitor in oil and gas wells, which gives us a hint or which gives us a clue that we are having flow assurance issues, which is the tubing head pressure and casing head pressure. This is especially true if you do not have any packer in place. So you should monitor the trends of these two variables. So will give you like an indication if you are having downhole problems or not. Plus, with the knowledge of the rate, you will know whether your production declining in the accepted rate or not. So actually, we monitor all of these data and plug them into flow assurance models or dynamic models in order to create all of these nifty studies that will enlighten us and gives us a great insight in our problematic field. So now we will take it a bit slow, and we will take a look at the two approaches into taking a look at the flow assurance issues or the production modeling in general. We have two different approaches. The first approach is the classical production modeling or the classical flow assurance approach. And we have the dynamic or the more modern approach. So let's take a look at the first. So the classical flow assurance or the classical production system modeling, actually it divides the model or it divides the production system into two parts. The first part is going to be the inflow. The second part is going to be the outflow. And the intersection between those two parts will give you the flow rate and the pressure. The flow rate and pressure, this is the anticipated operational condition for the Q and the P. And there are some issues that are related to this classical model. If you take a close look, or if you go back to the oil and gas or the production engineering literature, you will find these classical models were developed in an era where the computers were not developed very well. Plus, having a personal computer in the work was considered as a luxury, not a necessity. So this gives you an insight of the limitations of these types of models. One of the most severe limitations of classical modeling is actually there is no relation with time. The classical models, actually, they are composed of two parts. The first part is known as the inflow performance, the IPR, and the second part is known as the mechanical energy equation. There is only a single term on each one of these equations that the time occurs. However, the occurrence of the time is implicit. I am talking about the flow rate plus the velocity. So these two terms actually, they are related to time. However, they are implicit. There is no integration with time in these two equations, meaning that no matter the way you solve this equation, the equation itself will not reveal the performance of your production system with time, because those equations are steady state. They are not dynamic state. So this is the first and one of the major drawbacks of using classical modeling. It's not related to time. Meaning that if you want to predict the performance of production system 2 years or maybe 10 years from now, you cannot do that because these equations are not related and they are not integrated with time. The second and one of the severe limitations of these type of systems is the reservoir representation is very simplified, meaning that the reservoir representation is made up of a single equation like this one, like the productive index, where the full performance of a reservoir is existing in these three terms, which is the Q liquid, the reservoir pressure, and the PWF, which is the flowing bottom hole pressure. So can you imagine the reservoir, the complexity of the reservoir, and the specialists and the engineers have managed to minimize the complexity of reservoir into these three terms, meaning that there are a lot of simplification and there are a lot of assumptions that have put in these types of equation. So that's one of the major drawbacks for the classical production system, because the reservoir is simplified too much. In the current or in the dynamic approach for flow assurance and production modeling, we usually tend to use numerical reservoir simulators that are integrated with the wellbore simulator or with surface connections. This will give us a performance for the reservoir and the insight for the reservoir for with time. So this is the major difference. Plus, related to the flow phenomena itself, the modeling of the flow, it's not complex enough, meaning that there is no complex phenomena can be modeled using the pressure, the mechanical energy equation and the classical modeling approach, because these assumes that the mass flowing in is the same as the mass flowing out. So they are assuming the pressure, the conservation of mass. However, in most production system, a lot of different things that are happening and they are dynamic. For example, you might have gases going from gas to liquids like condensate, or maybe you're having like H2O vapor going from vapor state into liquid state, and they are just very complex to model in flowing phenomena wise. So the dynamic modeling approach will be best suited if you are looking for complex phenomena to be modeled. For example, one of the most important phenomena in flow in oil and gas industry is the slug flow, where most of the wells at a specific time in their life, they will start to flow at this pattern. However, this pattern is very hard to control and it will impose a lot of issues for the operators. For example, you can have separator issues, you can have ruptures in the flow lines. If you have the flow lines, they are not managing the pressure correctly. Plus, you will have all of these different issues. If you want to model the development and the complexity of the transferring slug from the bottom of the hole to the surface, the classical production modeling approach will not do the justice, because it's not related with time. Plus, it cannot give you those complex phenomena. Usually, these complex phenomena develop with time, and the classical production system model is not related to time in any way. So now let's go back to the modern or the more proper way into creating flow assurance studies. So in the 1980s, a software has been born. The software was, the name of the software was Olga. It was developed by IFE and Scientific, and it was backed by Statoil. This software actually initially can do simulation for oil and gas flow lines, but now that software, after 40 something year later, this software actually is capable of modeling all of the challenges almost in oil and gas industry. So basically, Olga is now as the industry standard in flow assurance studies, and regarding all of these design aspects in oil and gas assets and oil and gas projects, and during the different phases in the life of the field. So let's see what Olga provides for us, or what dynamic simulators like Olga provides for us. The most important thing, Olga, is related with time. So all the results you will get, all the results are related to the time. So different aspects of your production system, like slugging, like liquid loading, and like hydrates, they change with time. So their characteristics and their behavior will change with time. So this was not possible before the era of Olga. You can do slugging modeling in Olga in very complex and very effective way. You can do hydrate management, and you can do some mitigation with hydrates, like deploying different mitigation strategies. You can predict wax deposition, and you can do mitigation strategies as well. You can see if your production system can deal very well with ramp ups and ramp downs. So this is very important. Plus, if you have any artificial lift systems that are installed in the field, you can just study the stability of this artificial lift system, because in the dynamic, because in the steady state or the classical approach, the ASP and the gas lift design, they are just static design. It does not have any troubleshooting, or it does not have any issues growing with time. However, in the dynamic modeling, this is very prominent, and it's very important to model. Plus, if you are having liquid loading in the gas wells, you can study that very easily inside softwares like Olga. Plus, if you have some wells that are experiencing some bad flow, or they are experiencing some short-term shut-ins, you can model the cleanups as well. And the most modern studies in the area of flow assurance is linking the reservoir, or integrating the reservoir and production. The production can be wellbore, surface facilities, and etc., etc. Once you link all of these components together, you will have the full effect of the transients or the dynamic, starting from the reservoir and ending at the surface facilities. You can do a lot of case studies with Olga and the dynamic simulators. However, for the shortness of time, we will take a look at basically 3 case studies. The first case study is the slugging in a hilly terrain. The second case study is a test separator, and the third case study is a wax deposition. So let's take a look at the first case study. I will show you the slides, and then we will move forward to the software itself. We have a specific case of a pipeline of almost 8,000 meters in length, and there is a hilly terrain that this pipeline is passing on. This chart actually represents the flow line terrain. So you can see there's ups and downs. So ups and downs actually can disrupt production and can induce slugging. There is a cluster of wells that's connected to the start of the pipeline, and the end of the pipeline is connected to to an offshore floating platform. Slugging actually is expected in these types of situations. However, the severity of the occurrence and the frequency is not known. So Olga is used, or dynamic simulation software, they are usually used in order to investigate the slugging and evaluate different mitigation strategies. So without further ado, let's go ahead and launch up the first case study. So this is the first case study. Now you should have a screen, a software screen in front of you. Please, if you do have it visible, please comment in the chat box if you can. Thank you so much. So let's go ahead and proceed. Since we have short time, I will just make everything simple. So basically, you have a source for inflow or the source for production coming from M. Inlet, just think of inlet as just the start of the pipeline itself or the start of the production cluster itself. The branch is the pipeline itself. If you double click on the branch like this, it will show you like the different terrains and the different profile for the production itself or the production pipeline itself. So you can see like there is like ups and downs in this production pipeline. And the pipeline ends at the outlet. The outlet actually represents the floating platform, plus you have a single valve on the incoming flow line. So let's go ahead and try to run the simulation on this and see if we have any slugging happening in the well. And as we were talking about in the slides, softwares like Olga, which can do dynamic production simulation or dynamic production system evaluation, they usually tend to integrate all the results along the time. So if you go to the integration, you can see the simulation time is set to 2 hours. However, you can extend to this simulation or shorten it to any specific time you desire. Some simulation can go up to 60 days. And some simulations are just short as 30 minutes. So it all depends on what you are trying to do. So without further ado, let's go ahead and run our simulation. Once Olga reads all of these files that are related to it, and now it starts to spit out the results. By the way, you can start plotting the results before even the simulation finishes. So let's go ahead and do that. By the way, Olga provides different plotting or different view of the data. For example, one of the most popular view is the trend plot. Trend plot basically provides you with a single location, and that location will be plotted with time. For example, let's go ahead and do our plotting at the outlet. Let's plot the pressure. And you can do a lot of plotting. For example, you can plot the liquid content. You can plot one of the most important things, which is the holdup. Holdups actually will provide you all of the fraction of the liquid to the fraction of the gas. So this is very important to plot as well. And one of the most important things to plot is the identification. The identification as actually this is the flow regime identification. So you can plot that as well. Once you select all your variables, now you can view the results. For example, if you have the results showing, you can turn off some of the curves just to focus on some of them. For example, you can see there is definitely some fluctuation in the pressure and in the holdup in specific locations in this production system, meaning that there is definitely some slugging that's happening in this system. By the way, if the units is not to your likings, you can just go ahead and change the units from seconds to hours. Since we started to plotting before even the simulation finished, you can just go ahead and refresh the plot and receive all of these new data. This is definitely some slugging happening in the well. You can do a lot of plotting. For example, you can just go ahead and plot the flow of the gas or the flow of the liquid. Let's go ahead and plot the content of the liquid in the flow line itself. This is going to be plotted with time, and you can choose whichever unit you like. You can plot the number of the slugs that's existing in a specific product in this system. So you can have like a basic idea of how many slugs is being generated. So let's go ahead and select the number of initiated slugs as well. Now you can see the liquid content in this flow line, which is represented in the blue line or the blue curve. You can see there's a great fluctuation in the content of liquid along the flow line because there is instability that's happening in the well or in the flow line itself. By the way, you can just turn off everything and plot the number of the slugs that are existing in the system simultaneously. For example, you can see the number of the slugs are actually counted in the software. For example, during the first hour of production, you can just zoom in. The first hour of production, you can see there is like 20 slugs in the system. This goes up and down depending on the operating condition and the change in the environment and in the operating environment itself. So you can do a lot of customizations to this. So let's go ahead and try to manipulate the choke size itself. So the choke size is actually fully open. If you make that quarterly open and like 0.25 open and rerun the simulation, you can evaluate different strategies for the topside choke. And you can go ahead and do some trials and errors regarding this area. So you can see like different mitigation strategies. Now you can see the slugging is now less severe because we have choked down on the production system a little bit. Now, this is the first case study, which is the train slugging. Let's go back to our slides. The second case study we will take a look at is actually the test separator or the production test separator. We will open up this file. This test separator is connected to two groups of wells. A single group of well where they are producing just normally, and then there is another well that's offline. We will be connecting that to the separator, and we will be monitoring different aspects of the separator, and we will see if there is any carryover in the system and if there is any instabilities associated with it. So I will launch up the production separator project. So this is basically a production separator project. Just do not get off guarded by the complexity of the project. This is, by the way, this is very simple to create. So the first of the group, you have the well clusters. So the well clusters is flowing to this test header. And then you have another group of wells or another single well, which is offline. So, so what will happen if we open up this offline well? How it's going to change the different characteristics of the flow in the separator itself. So before we open up this well to production, let's go ahead and see the different performance of the separator itself. So let's go ahead and create a profile plot. By the way, there is a lot of variables you can plot. So one of the variables I usually plot is the liquid level in the separator itself whenever we are working with the surface facilities like this, plus the content of the gas in the liquid line, or sorry, the content of the liquid in the gas line. And you can do the opposite. You can just monitor the content of the gas in the liquid line as well. So this will give you an indication to the carryover and the blow by. So you can see with time, since the simulation has not finished yet, so the simulation is 12 hours. Now the simulation is done. Let's refresh everything. You can see there's a smooth operation in the separator itself. So the liquid level is sitting at 1 meter height, plus there is very little liquid content in the going out with in the gas line. It's usually less than 1 barrel per day. So it's very little and it's not noticeable. So let's go ahead. Once we had this results, let's go ahead and open up this flowing well to the production stream and see how it will differently affect the production separator. So once I change the status of well from online to from offline to online, let's see how that will affect our production separator. Let's refresh everything. Now you can see the separator now starting to have an issue. For example, in the previous example, or in the previous situation, the liquid level, which is denoted as the red line, it was smooth in the previous example. Now the liquid level is now starting to fluctuate, meaning that there is sudden open and closure in the separator valves, meaning that the well that I have opened to production is tripping my separator, or making my separator experience some unstable production. So if you are having a thought on putting this well on production, so you should double think of this before you put it online. Maybe you can put it online with different stock configurations, so you can do all of these nifty studies, and before you put it on production, you can do this type of simulation so you can see the stability of your production system. So this is the second case study. Let's go ahead and move to the third case study, which is the wax deposition. So we have this pipeline, which starts from the inlet and ends at the outlet, with the wax deposition and wax capturing, variable capturing is already enabled. So let's assume the inlet is the start of the pipeline and the outlet is the end of the production facility on the top. If we double click on the flow line on the branch itself, you can see the flow line is just a single horizontal smooth line. By the way, if you have like actual elevations, you can import this as well. Let's go ahead and now try to run the simulation by running on, click on run. Once the simulation is running, let's go ahead to the integration. You can see I am running the simulation for 10 days. So it all depends on what you are trying to do. So before we start to get some results, let's go ahead and do some plotting. By the way, whenever you're working with deposition plots, there is a plot called profile plots, where it plots a specific variable with length, and you can change it with time as well. So this is very useful whenever you're working with depositions. So let's go ahead and try to plot the thickness of the deposited wax on the inner wall surface. By the way, you can change the unit. Feet is just a very big unit for this type of depositions. We usually use inches or millimeters for these. So once we did this, we'll click on OK. And now you do not see any deposition because the start time is 0 seconds, meaning that this is before the simulation starts. Before we do anything, we will go to from second to hours. I will refresh this plot, and then I will move this slider so I can see the thickness of the wax bed is developing with time. If you want, you can capture these thicknesses with time. For example, you can capture it and then you can just move the slider and then capture again. So this will give you an indication how the wax is being developed over the time. So the most important question and answer is in this situation is after. So let's change the length to meter as well. So after the length of 2,200 something, before this length, there is no wax deposition. So we need to know why there is no wax deposition in this area and why it started from that specific length. So in order to know why exactly, you need to plot two more variables. So the first variable you need to plot is the temperature of the fluid itself that's been flowing. And then the temperature of wax appearance, or it's known as WAT, wax appearance temperature. So you will plot that as well. These two lines, whenever they cross, it will give you an indication where the wax will start, because the wax appearance is actually as dominant by temperature. There is a slight effect from the pressure as well. However, the temperature is the like 99% dominant variable in the wax deposition area. So basically, you can see why there is this section does not have any wax appearance, because the temperature is just not enough to deposit any wax. And then once you cross this crossing line, the temperature is favoring the wax appearance. So actually, we have reached the end of this today's session. We will meet tomorrow. Tomorrow, we will be talking about oil and gas wells and how different flow assurance case studies can help us understand different